We know that we can represent certain functions as power series. So let's talk about that now. This is like normally what we call the power series representation. So let's look at what we did before. So we know that a power series, the standard form of a power series, we can write it like that. Um, so the Cn in some kind of coefficient and x minus a to the n. This is a standard form. So if you look at first few terms, the first term is C naught, and then we have C1 x minus a, and then C2 x minus a squared, like that. So that's the kind of idea. That's what we call power series, and you can see these are all powers of x minus a. Now the interesting observation is this. So you can see that for any x, for which I'm going to call this an, because you can see this is just a number. So an. So let's call an for which, for any x for which the series an converges. So what's going to happen? Let's say you pick a x, the series converge. So that means what you can do is you can write this as a function because it's converged to some value. So we can write that value as a function value. So what we normally do is we can write we're gonna say okay, fx equal, because that's gonna converge, we write that. So we say c naught c1 x minus a, so like that, c2 x minus a squared, like that. So because if for any x, if the series converges, then it's going to converge to a value. So then that means you can collect all those values, so simply create a function. Okay, so because you pick a value, pick x value, so you get a value. So like that, then you can see you're going to get like a bunch of values like that. So you can see, so it's going to define a function. It's going to define a function. That's the function it's going to define. So for each x, there's a value. For each x, there's values, and that one we can represent as a function. So good. So that means we can say, let's try like that. We call uh, we call this series. We call this series. We call this series. We call this series is the power series representation. Power series. Power series representation. Power series representation of fx. Okay, so that's the idea. So it's a very simple idea. So if there's a function like that, then we call that is a power series representation. Power series representation. So we go kind of backward. Power series representation of fx. Okay. So simply what we mean here is, let's say fx. So this is the power series representation. So whatever the starting value, let's say 0 in this case. Yeah. So this is the power series representation. Actually uh, about 8. Um, because it's depending on what value you pick. So that's the kind of idea. It's just a very simple idea. So let's see. So and then we can start with a several common one. So we start with this interesting geometric series. So we know that for absolute value x less than 1, we can have 1. If we start with 1, and then we every time you multiply by x, so x squared, x cubed, like that. So you can see that when absolute value x less than 1, that's a radius of that's r value. If r less than 1, we know that the geometric series converge. Okay, so we know that the r absolute value r less than 1, the geometric series converge. Geometric series converge. So it's converged to a over 1 minus r. In this case, a is 1, the starting value. And the r is x, so it's so 1 over 1 minus x. You can see this is a function. is a function, and x not equal to 1. Okay, so that's a function. So that's the idea. So that means you can write fx, in this case 1 over 1 minus x, as a power series. Um, Good. So this is like very common one. So let's write it like this, because we can use this a lot. So 1 over 1 minus x equal to 1 plus x squared plus x cubed, like that. So and then you can write this as a power series. So in going from 0 to infinity, and you can see this is just x to the n. We start with n equals 0, then you get 1, and this is valid for x, absolute x less than 1 only. It does not valid outside. It's not going to converge, we know that. Good. So this is the major result of this discussion, because we can use this a lot to generate a lot of other series. And then what we normally do, we can do like interesting things. So I'm going to call this is actually one, series 1. When I say series 1, that's what this means. Now what we can do is we can replace x by negative x. This is like a composition. So then when you do that, what's going to happen? And you can see that so you're going to get 1 over 1 plus x, 1 over 1 plus x, which is simply equals to 1 over 1 minus minus. So you replace x by minus x. So wherever you see x, you can put minus x. So that means this is minus plus, and then this is also minus x squared, and then this is minus x cubed, like that. So that means if you write the series, what's going to happen in going from 0 to infinity, negative x to the n. So you can split this negative x to the n, you can split this negative 1 to the n, x to the n, like that. So then we have this second series, 1 over, so this is good to remember like that, because this is very useful. 1 over 1 plus x, this is 1. What's going to happen? See, whenever you have odd power, it's going to be negative. Even power, no change. Odd power, negative, like that. So like that. So this one you can write as sigma n going from 0 to infinity, negative 1 to the n, x to the n. Interesting enough, is also valid only for absolute x less than 1. So that's the second series. So these two are very useful. So it's good to remember like that. Good. Okay. Yeah, I'm gonna call this is series number 2. Okay, so now let's see what else out there. So there are a lot of things that we can do with these two. So let's look at some of the applications. So let's start with the algebra of power series. How to do certain algebras. So I'm gonna call this algebra of power series. So we learn before that. So you can add two series, or you can subtract, and then also you can multiply, also divide. You can also divide, multiply and divide, so be careful when you divide. So you can do like even the long division for that. And then the most important one, what we're going to do is we're going to take the composition. So take composition, or what we normally call the substitute. We already did that. So we substitute x by negative x, like that, substitute. So this is the most common one actually we do. And then also there's an interesting one. That means you can take the derivatives. So differentiate, or take the integral. So integrate. So we can do these things to get new ones. So that's the kind of idea. So this is like very common practice. So we have this important theorem. So let's start uh, with this. So what it says, if fx equal this power series Cn x minus a to the n. I'm not gonna specify the n value because depending on the function, has a radius of convergence r, radius of convergence r. So let's say this has a radius of convergence r. Then what we can do is we can take the derivative of this function. So that means f prime x is simply you're gonna take the term-wise derivative. So it's a d by dx. Just take the derivative of this series, sigma Cn x minus an. So what we're gonna do, we're gonna switch uh, and then we're gonna take the derivative. So it's a we're gonna take the derivative inside. So Cn is just a constant, so we just put it there just for simplicity. What's gonna happen is we simply take the derivative of this part uh, by the chain rule. Good, that's the first result. So what it says that you can simply take the derivatives of the series. And then also the second one is you can also integrate. So we can integrate the function on this side, and then it's going to represent the integral of that. So that means if you know to find the power series of the derivative, power series representation of the derivative, what you can do is you can simply take the derivative of the power series. So the same thing, if you need to find the power series representation of the integral, you just take the integral of the power series. So it's a very interesting idea. So sigma Cn x minus a to the n dx. So pull the sigma out. You switch. That's how you do. You switch the two. So Cn x minus a n dx. Okay, so you switch the two. Good. And then the interesting part, if has a radius of convergence, then uh, these two has the same radius of convergence. So it does not change the radius of convergence if you take the derivative or if you take the integral. So that's a very interesting result. Has the same radius of convergence. Has the same radius of convergence r. Okay, has the same radius. So that means when you take the derivative, so integral, it does not change the radius of convergence r, but it may change. It may change the interval of convergence, because you have to be careful with the endpoints. You have to be careful with the endpoints, because it can especially when you try to take the derivative, it can change, it can add, uh, it can lose the convergence. So you have to be careful with that, because when you take the derivative, there's an end term coming to the top. So that means it's gonna change the p-value. Once you change the p-value, it's going to change the convergence. So you have to always check the new points, new endpoints, but the radius of convergence does not change. Okay, that's about that. That's all the theories that you need to know. So let's look at some examples. So we start with this one. So let's say example. Find a power series representation of the following functions. Find a power series representation, power series of the functions. So let's start with this. So what we're gonna find the power series. So the first one, let's say 1 over 1 plus x squared. So if you get a problem like that, what we can do, we're gonna see what's the connection between our non-power series and this one. So I'm gonna now like go with the basics. We always start with the 1 or 1 minus x because that's like common one. So let's say so how to handle this one. So let's say we know 1 over 1 minus x equal 1 plus x squared plus x cubed, like that. So this is always a kind of starting point unless something else is given. Xn, this is valid for x less than 1. This domain is very important. So we know that. Now what we're going to replace x by, so you can see what is the connection between the two, and you can see we have we have plus x squared. So that means you need to replace because you have to bring it to this form. You have to bring it to this form. So what we're gonna do is we're gonna write it like this. So it's a 1 over, because there's no negative sign, that means you have to put the negative sign, but you can't just put a negative sign, you have to put two negative signs. So we're gonna write it like that. So this tells you that that is the one you're gonna replace with negative x squared. Okay, so that means replace x by, so what we did, if there's a plus sign, you have to include two negative signs. If there's a minus sign, you don't need that because only minus sign is there. So you can kind of compare the two. So you can see x by negative x squared. That's where that's magic term coming from. So if you do that, then you can see 1 over 1 plus x squared is simply 1 over 1 minus x squared. So that's the term we are talking about. So you simply replace x by that. So we can do that. That means 1, wherever you see x, put negative x squared. So that means the second term going to be now negative x squared. And then plus negative x squared, and then negative x squared cube. Let's try the first few terms. And then we can do the same thing in the general term. So in going from 0 to infinity, negative x squared. So that means if you can simplify this a little bit, so you can see you can pull the negative sign out. So you can write it like that, and then x gonna be actually it's not square, so, it's n. So put the n there. So that means it's gonna be 2n. You can see there's a 2n. So this is 2, and then also now where this is valid, so you also need to replace that x by that common term also. That means what's going to happen here is negative x squared less than 1. So that's what happened. You see, you replace x by that also, and then you can solve this and find the x value. So now we can see we have the final answer. So because of that, you can see that 1 plus x squared. So we write it like that. You can see thus, just to complete the argument. So it is, so we can write the notation here. So let's write the first few terms. Is 1 minus x squared, and then we have plus x to the 4th minus x to the 6th, like that. Just few first few terms. So and then the notation is sigma n going from 0 to infinity, negative 1n x to the 2n. Okay, so how to simplify this? You can see this negative sign, you can disregard the negative sign because absolute sign, and then take the square root of both sides. So once you take the square root, it's simply going to be the same x less than 1. So that means that's still valid for the same x. That's very important part. So that's the final answer. You can see it's not that difficult, but there are certain things that we need to do. But once you practice it, it's going to be really easy. Okay, so let's look at the second example. So I'm going to do a couple of examples because this is something that you need to definitely need to know as the consequence of Calc 2. So next one. So let's see 1 over 2 plus x. So the argument is we can write because see we have to bring it to 1 over 1 minus x term. So there's no 1 here. That means since there's no 1 here, so what we do, we're going to divide inside by 2, or we're going to take 2 as a factor out. That means you divide everything inside by 1. That means the first term going to be 1, second term going to be x over 2. That's the first step. You divide by 2. The second step, you need to introduce the negative sign. So what we do is a 2, 1 minus x over 2. So those are the two steps, but you can do in one step. So, and then after we do that, you can see it's very clear. Um, so this is the term you're gonna replace. Okay, so negative x over 2. So now you're gonna go back to the original series, the common series, and do that. So that means negative 1/2 you can write outside because that's a common term, and then go to the general power series, the series 1 that we talk about at the beginning, and replace x by negative x over 2 to the n. Now we can simplify this a little bit. So this is sigma. So we have negative 1n, and then we have x to the n, and also 2 to the n. But you can see there's a 1/2 outside. That means you can bring it inside. That means it's going to be plus 1. So that's that plus 1 coming from, because there was a 1 outside. Good. So that's the final answer. Now, and then also the n value is still the same in going from 0 to infinity. Let's check the domain where this is valid. So it's a negative x over 2 less than 1. So you replace x by that. Now what we can do, you can ignore the negative sign, and then you multiply by 2. Once you multiply by 2, you can write this one as x less than 2. So that means the interval is now negative 2 to 2. So that's the new interval. That's where this is valid. Negative 2 to 2. Okay, so not like before. So it is from negative 2 to 2. So it's changed the interval. Good. So that's the answer. So let's do another one. So let's slightly change this problem. So let's say you need the power series for x to the 5th over 2 plus x. So if you get a problem like that, if you want to start this from scratch, what we're going to do is we don't worry about the x to the 5th term, because just a simple power. So what we normally do is we're going to start with the bottom, x plus 2. So these are all the steps that you need for a problem like that. So we're going to pull the x5th out and then write x plus 2. And then we can write x plus 2. We do what we did before for this problem. So that means we can write this one as before. So that means it's going to be 1. Pull 2 out. Write 1 minus x over 2. Like that. And then plug in that to the series. So once you plug in that to the series, so you're going to get as before. So since we know the answer, I'm going to skip that part. So we can see that this is x to the 5th, and then our answer was sigma, and going from 0 to infinity, negative 1 to the n over 2 to the n plus 1 x to the n. That's what we get. And then what we can do, we're going to bring this term inside. So that means you simply raise the power. So that means is sigma n going from 0 to infinity, negative 1 n. What happened here is x n, you're going to add 5 more. And then this 2 to the n plus 1. So that's what we have. And when you do that, it doesn't change the interval. Interval is still the same. Good. So now, so if you write the first few terms, you can see that. So let's write the first few terms. Let's plug n equals 0. So negative 1 to 0 means 1. So if you plug n equals 0, so you're gonna get from the bottom you get 1/2. So you get 1/2 x to the 5th minus, if you plug n equal 1, you're gonna get 1/4 x to the 6th, like that, and then 1/8 x to the 7, like that. That's the series you get. Um, and then also this is all valid for x less than 2. You can also write this series using like here you can see that x to the n plus 5. If you want to start with xn, you can do that. So let's see how to do that, how the argument gonna work. So we also know that there's a sign term, so we can leave it like we don't write the terms. Let's say you want to write this x to the n. So if you want to say x to the n, you can see you have to start with n equal 5 now. Infinity does not change. And then think about the sign, because when you apply n equal 5, to get a positive sign, it cannot be n. It has to be n minus 1 or plus 1. So something like that. It can be plus 1 or minus 1, doesn't matter, because now you can see that you get a positive sign. But you want to make sure that you also get 2 to the when you plug n equal 5, you want to make sure that you get 2 to the first. So that means it is not n, it should be n minus 4. So that's like another way to write the same series. Still again this one valid. So yeah, so that's something you can do, and we can talk about this one later, like how to do that. So actually I introduced a technique called the seesaw method. We can discuss that in the next problem, and how to use the seesaw method and get this answer. So yeah, it's called the seesaw method. uh, uh, Yeah, this is something I introduced like last year. That's like kind of very powerful way to get the answer. So, but it's up to you, like how you write it. You can complete write these first few terms, or you write the general term like that. So there are 3 ways to write this answer, either this way or that or that. So all of them are correct. Okay, let's go to the next problem. How about this one? Let's say you have x minus 1 over x plus 2. So you can see the bottom is still the same, but you have x minus 1 here. So if you get a problem like that, you can do the log division first, or just do a simple manipulation. This is the manipulation what we're trying to do. So what we can do is you try to create the term in the bottom. So that means you're gonna add 2. We're gonna say x plus 2. You're gonna add 2 and subtract 2. When you subtract, it is negative 3. So you can write it like that. Now what we can do, we're going to collect the terms. So that means if you collect this term, if you divide, you're going to get 1 minus 3 over x plus 2. So you can write it like that. And then it's just 1. So that's just 1. And for the 3, it's just a multiply. And then we know this one already. So we can replace by that. So that we can do. So that means we can write this one as 1 minus 3 times. Since we already know the series, so we can write it. If you don't know, then you have to do that first. So it is negative 1 to the n, and then 2 to the n plus 1 xn. So we can do it like that. The other thing, so if you want, you can also pull the negative sign inside. That's not a must. And also this is only valid for the same domain, so it is x less than 2. If you want, you can pull the negative sign inside. So if you do that, so 3 uh, n going from 0 to infinity. If you pull the negative sign inside, you just need to add 1 more. So let's say plus 1, and then 2n plus 1 xn. This is valid for x less than 2. So it's a very simple algebra, but this is how you get the power series representation for that. So let's look at the next example. So let's look at this one. So it's a E. Let's say we need the power series for x cubed over x plus 2 squared. So this is the special term that you're gonna see. That is squared. So how to kind of relate this to what we already know, and then you can see that when you take the derivative, when you take the like if you have 1 over x, and if you take the derivative of that, So we see, so we can take d by dx, x to the negative 1. So that means the derivative is negative x to the negative 2. That means a negative 1 over x squared. So we know this result. So that means if we have 1 over x, if we take the derivative, it's going to square the term in the bottom. So that's the kind of idea that we try to use. So that means if you start with 1 over x plus 2, and if you take the derivative, it's going to increase the power in the bottom. So let's start with that. So that means we can start with 1 over x plus 2 that we already know. So which is sigma n going from 0 to infinity, negative 1 n over 2 to the n plus 1 xn. This is valid for x less than 2. Now what we can take, we can take the derivative. Okay, so we can take the derivative. So let's see how the next few steps works. So by differentiation, and we also know that it does not change the radius. So take the derivative, so d by dx, 1 over x plus 2. So we can take the derivative of this series n going from 0 to infinity. Yeah, there are some writing, that's why this is kind of long. And then what we normally do, we can switch the sigma with the actually before we do that, let's try the first term of the series. So you're gonna see the why we want to do that. So it's a derivative. So before we do that, I'm gonna write the first term. What's the first term? When you apply n equals 0, and you can see that you get 1/2 plus, let's try the rest in going from 1 to infinity. So it's a very important step. You're gonna see why we gonna do that. 2n plus 1 xn, and then now let's try to take the derivative. So we write the first term, just the first term. Okay, when we want to do that every time we take the derivative. Now if you take the derivative of the left side, what do you get? Remember, we can write this one, we can bring this to the top, so we can write it like that. We're gonna write it like -1. So then you can just use the power rule. So if you use the power rule, you're gonna get negative x plus 2 to the -2, and the derivative of the inside is 1. So that's what you get. And on the right side, you can see the first term is 1/2, so you get a 0. And then you're going to see if you take the derivative of the rest of the functions. So this is very easy. So you're going to get -1 to the n, no change, no change. These are constant. What you take the derivative here, you're going to get n x n minus 1. That's what you get. Now, so you can write this term. So there's a negative sign here. So we're going to say a -1 over x plus 2 squared. And on this side, we can write it like that, n going from 1 to infinity, -1 n, 2 to the n plus 1, n x n minus 1. Now, to remove this negative sign, what we can do is we can multiply both sides by negative. So if you do that, then you're going to see this is 1 over x plus 2 to the square. So sigma n going from 1 to infinity, you can say n in front, and this is -1 n plus 1, and in the bottom 2 to the n plus 1 x n minus 1. That's what you get. So you can see this change here because you multiply by one more negative sign. Now what we do is we simply multiply by x cubed both sides. So if you multiply by x cubed both sides, So you can see that x cube over x plus 2 squared. So you simply increase this 1 by 1 to infinity n, negative 1 to the n plus 1, 2 to the n plus 1. X, you just add 3. It's going to be n plus 2. So that's what happened. So the next thing would be, so this is perfectly fine, so we can leave this as the answer. But if you want to write this one as a power of x to the n, there is something that you can do. So here I'm going to use my technique that we call the seesaw method. So what the seesaw method is, you can so it just work like a seesaw. So you know that in the seesaw, when one side goes down, let's say by 2 feet, this side exactly goes up by 2 feet. So, and then you can see the pivot does not change. This stays the same, but the two sides go up, down by the exact same amount. So we can use the same argument here. So that means if you want to bring x plus 2, n plus 2 to n, what you want to do is you're going to bring this one down by 2. All the terms are down by 2. And then what you want to do here is you want to bring outside up by 2. So that's the idea. So that means if you do that, what's going to happen? This is simply going to change like this. So sigma, this say n, you up by 2, that means you're going to do 3. Infinity does not change. Everything inside you're going to subtract 2. So that means this is going to be n minus 2. And then in the bottom, this is 2 n minus 1 because you subtract 2, and then negative 1. So you can see, you see n plus 1, this is going to be n minus 1. Actually, because since this is a sign change, even you can leave n plus 1 here if you want, because if you change by a even number, it does not change because you subtract by 2 or add 2, so it doesn't change. So you can even leave n plus 1, but you can subtract without any problem. And then here this can be x to the n. That's this interesting part there. So that's the, so try to use that. This is what we call the seesaw method. Seesaw method. So there's a video. So if you just search that, you can find this in my uh, in the videos called seesaw method. I did that for the differential equations. Okay, and then again, so we take the derivative. So you can see the radius of convergence does not change. So there's still x less than 2, but you need to check the corners. So because in this time, because since we take the derivative, it's gonna introduce n. So, but since this is open, there's still no problem. It's still open. But if there was a closed corner, it may be not the case anymore. But here it doesn't change. So that's the final answer. So you can leave the final answer in any way, any option. So either the first method or the second method. So it's up to you. Okay, so that's the kind of idea how to do a problem like that. So let's do another one that have like a log function. So we have, let's say we are looking for x3 ln x plus 2. So what is the idea here? We know that, so this is the important result here. We know that if you take the integral of 1 of x plus 1 of x, so this is simply natural log x plus c. So if you want, because this means that this is a whole domain for x positive or negative. So if you just write one of them, that's still okay. It's valid. So that means if you need just a half of it, because what happened here is we consider the whole domain. Um, so what is this absolute sign? So that means we remove 0, and then you can see it's valid for both uh, positive and negative x. So that's the only thing we did there. So that means if you just need one side, you can still do that, but you have to be careful. You're going to mention what value you are talking about. But if you know that this is definitely positive, then you don't need the absolute sign. But we know that in the domain we are talking about absolute x less than 2, you can see that x plus 2 is positive. So that means you can relax the absolute sign here. Good. Uh, good. So again, we can start with 1 over x plus 2 series. So if you don't have it, do that first. So it's going from 0 to infinity, negative 1 to the n, and then 2 to the n plus 1 xn. This is valid for x less than 2 that we know. Now what we do, we integrate. So by integrating with respect to x, actually that's the only variable. So what happened here is when you integrate 1 over x plus 2, you can see that you're going to get ln x plus 2. I don't write both, I just write only the x plus 2 part without writing the absolute sign here. Okay, so I intentionally did it because it's going to give you half of them. That's okay. So like I'm going to consider only the positive side. Good. So now, so what we can do on the other side, you're going to integrate. So let's integrate the series. So I'm going from 0 to infinity, negative 1 n to n plus 1 x to the n dx. So what we do is we're going to switch the sigma and then also negative 1 and there's no x there, 2 to the n plus 1 there's no x there, so we can say x and dx. So if you do that, then you can see you're going to get this. So sigma n going from 0 to infinity, negative 1 n, 2 to the n plus 1, x to the n plus 1, n plus 1 plus c. So you get c there. Now what you want to know is we need to look at some of the results and try to find c. So the best thing we do is we normally plug in x equals 0, so then you can take out the series term. Okay, so we do that. So let x equals 0. So if we do that, then what's going to happen is you can see on this side you're going to get ln 2 only. You get all the term 0 plus c because there's an x term involved there. Good. So this says that c equal ln 2. Now what we can do is we can plug in that. So we're going to get this. So we have ln x plus 2 equals c was ln 2. So we write that first and then the rest of the series. So sigma n going from 0 to infinity, negative 1 n over 2 to the n plus 1. And then also you can write n plus 1 here if you want, and then this is x to the n plus 1. Now what we can do, so we have that, and again this is valid for x less than 2, and then what we're going to do is we're going to multiply by x cube. So multiply by x cube. So if you do that, you get x cube ln x plus 2. So you're going to get x cube ln 2 plus sigma n going from 0 to infinity, negative 1 n, 2 to the n plus 1 over n plus 1 x to the n plus, so you have 1, so you get plus 4. And you can see that so this series, so this is what the series you get, and then you know the interval which is from negative 2 to 2, and you can see that if you plug in x equal 2, you get the alternate series which gonna converge. Uh, so that means the interval now gonna be, so this is valid for x for open at -2 but close at 2. So you're gonna get a new point there. Um, because you divide, it's going to be better converge than this original one because you're dividing by that, so it's going to slightly change the p. So it's going to be it's going to get like a um, much smaller series, so it's going to converge. So that's the difference. It doesn't change the r, but it changes the interval because it's going to get alternate series which is going to converge. Good. So that's the kind of idea. And then also, if you want to write this one using xn, that we can do. So you're going to bring down by 4 and then up by 4. If you want to do that, so this is the final answer. If you want to go in that route, so you can see that. So this is x3 ln 2, and then here what's going to happen? You're going to down by 4, up by 4, outside up by 4. So if you do that, you're going to get n equal 4, we add 4, infinity. And this is 4 is a even number, so I'm not going to change this. So I'm going to say li n to n because it does not change. But here, you're going to down by 4, that means 2n minus 3 because you subtract 4. And then also we have n minus 3, but this is x to the n. So that's the interesting part. Okay, so that's the final answer using a new index, but you have xn term. But that's not necessary, but you can do it if you want. Good. So let's do one last problem from that. So let's do a like integral problem. So how about this one? So let's say this one. Try to evaluate an integral. So let's say 0 to 0 to 0.5. Let's say 1 over 1 plus x cubed dx, something like that. So that's like a slightly different problem. So again, if you get a problem like that, we're going to match with one of our non-series. So we're going to start with 1 over 1 minus x. So this is sigma n going from 0 to infinity, xn. This is valid for x less than 1. So you can see the values, both values are inside that, so that means there are no problems here. That's where the series converge. Now what we can do, we can replace this one by, you can see -3, negative x cube. Okay, so we do that. So replace x by negative x cube. So we have 1 over 1 plus x cube, which is 1 over 1 minus x cube. So that means if you write this series notation and going from 0 to infinity, negative x cube n. So you can pull the negative sign out. So -1 n x to the 3n, so you get, and this is only valid for x less than 1 because it's get negative x cube. That's what you get, negative x cube. And then what you can do, you can take the cube root, so you end up getting this. Okay, so it's the same thing. Good. So now we have this series. So what we can do is take the integral. So let's integrate. So we have 0 to 0.5, 1 over 1 plus x cubed dx. So it is 0 to 0.5. So we replace the series by its integral by the series representation. So x3n dx. Switch the sigma. Pull the unnecessary terms. And then we're going to integrate inside. 0 to 0.5. And if you do that, you're going to get n going from 0 to infinity, negative 1 n x to the 3n plus 1 over 3n plus 1, evaluated at 0.5 and 0. So if you plug in 0, is 0, and if you plug in 0.5, you end up getting sigma n going from 0 to infinity, negative 1 n negative 1 n 3n plus 1. 0.5 means 1/2. So we can write this one as 1 over 2 to the 3n plus 1. So that's the answer. And you can see that this can converge because this is an alternate series. So converge by the alternate series test. Okay, this is interesting applications of this, because you can see that this is not an easy integral. If you want to do this using the method that we learned, you cannot do it. It's not going to work. 1 over 1 plus x cube is a difficult integral, but we have a series technique to do it. Okay. So let's look at these practice problems. So for example, the first one, if you look at the first one, you can see that there's no 1 there. So that's a very important term that we need. And also the negative sign. So first thing what we do is we're going to get the 1. So to get the 1, what we can do is we can pull 3 out. So if you do 4, if you pull 3 out, so you can say this is 1 plus 2x divided by 3. And then we know what to do. And you can see that you need to replace x by negative 2x over 3 in series 1. In series 1, remember the series 1, the geometric series. So that we do. So that's the starting point for that, and then you know what to do after that. So second one is easy. There's a 1 already there. So for the second one, you have to replace x by negative 2x squared first. Okay, so you can see this is x by negative 2x squared in 1. So that you can try the rest, but third one is really interesting. You can see it's quadratic. So what we normally do is we're going to factor this. So you can see the factors are x plus 2 and x plus 1. So then we're going to go for the partial fractions. So we're going to go for partial fractions. And then once you get the partial fractions, you're going to get 2 series, and then you're going to either add or subtract those 2 series. So that's how you do that one. So go for partial fractions, write 2 series and combine them. The fourth one is easy. You have to take the derivative. You can see that square there. So you're going to start with 1 over 1 plus 4x first, and then take the derivative. The fifth one is really interesting. You're going to see tan x cubed term. So the starting point for these kind of problems would be this observation. We know that if you take the integral of 1 over 1 plus x squared, so this is simply tan inverse x plus c, and you can find the c as we did before. You can plug in a value, for example x equals 0, and then try to find c. That you can do. So that's the first thing you do. You try to find a series representation for tan inverse x, and after you do that, you're going to replace x by x cube. That's the second step. And after you do that, and then you're going to multiply by x squared. So you can do. So the starting point would be look for the series representation for 1 over 1 plus x squared, and then take the integral, find the tan inverse, and then after you get tan inverse, replace x by x cube. And then you can do the same thing with for the last one as well. Okay, so those are kind of interesting examples for that. You can try some of them. Good.